Okay, so yesterday we talked about the two parts of a number and place values and rounding and some of those basics. And I know kind of basic for many of you. Today, though, we're going to take that next step and we're going to get through all of our operations with whole numbers just to kind of continue our review a little bit. We talked about having a number like 362 and the fact that that's just an abbreviated form of that number. That really this is 300s. I don't know where the N came from there. 300s and 6 tens and 2 ones. In that long form or in that full form, if you recall, it shows us that each digit is a count and a name. This isn't just a 6, it's 6 tens. So if we're going to add that, or we're going to combine that with another number, let's say we're going to combine that with 423. We'll write that one out in its long form, the full form. 400s and 2 tens and 3 ones. One of the things we've always been taught with adding and subtracting whole numbers is that you have to line up the columns, right? So the big question is why? Well, we talked yesterday about adding and subtracting and how when you add or subtract, you combine the counts and you keep the same name. And that means that to add or subtract, you must start with the same name. You can only combine things that have the same name. So when we're looking at larger numbers like this, what that means is tens can only be combined with other tens. Hundreds can only be combined with other hundreds. Ones with other ones. That's why we have to line up those columns. Once the columns are lined up, then we just go ahead and we can add down our columns. 300s and 400s make 700s. 6 tens and 2 tens make 8 tens. 2 ones and 3 ones make 5 ones. We get 785. Now some of you might be looking at that thinking, that didn't look quite right. What did I do differently from what you were taught to do? Yeah, I went left to right. We've been taught to go right to left, right? Why do we go right to left? Yeah. Normally, we'd start on the right, work our way back to left because we might have to carry. 479 plus 246. Starting on the right, working our way back to the left. 9 plus 6 is 15, but we can't have 2 digits in there. So we're going to keep the 5 and carry the 1, right? So now we combine the 1 with the 7 to make 8 plus 4. 12. Again, we can't have 2 digits, so we keep the 2 and carry the 1. Combine the 1 with the 4 to get 5 plus 2 is 7. Did I show you any alternative forms for adding yesterday? Not yet. We didn't get that far. Okay. Some days it takes me a while to remember where I was with each group. Okay. So that process of carrying like that is why we start on the right and work our way back to the left. But believe it or not, it's a relatively new process. Now, by relatively new, I mean like 150 to 200 years old. Before that was developed, one possible way of adding numbers, or adding these numbers, would look like this. Now, you don't have to, if you're taking notes, you don't have to write this down. You don't have to remember this. I'm never going to force you to do it this way. And I'll explain why I'm showing you this in just a minute. But a different way you could have done this is 4 plus 2 is 6. 7 plus 4 is 11, so 1, drop the 1. 9 and 6 is 15, so 5, drop the 1. 7, 2, 5. Now you can see it gets us to the same answer. It will work every time. My point for showing you that is not to change how you add numbers. It's to show you there's different ways you can do it. And we've always been taught there's a stereotype out there, there's only one right way to do math. No, there's only one right answer to each problem, but there can be several different processes. I could show you 4 or 5 different ways of adding whole numbers that work every time. Now, I'm not going to do it because I don't want to confuse you, but there's different processes out there. And I'm a realist. I realize that you guys have the calculators, you're going to use them. So at the very least, before you punch this in your calculator, I would hope you would look at this and say, hey, 479, that's about 500. 246, that's about 200. 5 and 2 makes 7. I'm expecting an answer close to 700. Now, this is how I estimate them. You guys will probably come up with your, I would like you guys to come up with your own way of estimating. Maybe this way works for you, maybe it doesn't. The key with estimation is, just like you know, there's no right or wrong way to estimate. You have to have a way to estimate that's easy for you, that's quick for you. Otherwise, you're not going to do it. If it's a lot of work to do, you're not going to bother doing it. And the reason it's important to me that you estimate this, or at least it's important to me that I estimate this before I punch it in the calculator at least, that I have these fat fingers and pushing the buttons on the calculators, I sometimes run into problems. For example, doing my 479 plus 246 wouldn't be uncommon for me to have something like this happen. 479 plus 246. What went wrong there? I missed a button. I didn't. When I went to hit the 4, I didn't press it hard enough, or I missed it. But if I'm not paying attention, 505, that seems okay. I write down 505 and I go on my way. But by estimating it here, I know 505 seems a little too small for comfort. I'm going to double check that. The other thing that happens to me a lot is this. 479 plus 246. What happened there? Hit an extra key in there. When I went to hit the 9, I hit the 8 also. Again, if I'm not paying attention, I write down 5,035 and pay the price for it later when something goes very wrong. That estimating helps me. The estimating doesn't guarantee I'm going to do it right, but it helps me to avoid some really, really major errors like that. Let's look at subtraction. Let's do something like 574 minus 243. Now I could write these out in their full form, their long form, and do what I did with addition, but I think you guys get the point at this point that the place values have to be lined up because addition and subtraction, you only combine digits with the same place value or same name. So once they're lined up like that, we can just go ahead and subtract. 5 minus 2 is 3, 7 minus 4 is 3, and 4 minus 3 is 1, 331. Now what did I do again? I went right to left. I went backwards. Normally we would start at the right and work our way back to the left. And again, why would we do that when we subtract? Yeah, in case you have to borrow. There's the word we're looking for. Because we run into problems like this one. We start at the right, working our way back to the left. 4 minus 5 can't be done. So what do we have to do? That would borrow from the 2. That's a 1. This is now 14. Now, a lot of you probably just thought you just put the 1 in front of the 4. That's fine. I'm just being technical, crossing it out and rewriting the 14. 14 minus 5 is 9. 1 minus 9 can't be done. So we're going to cross this out. This is 6, and this is now 11. 11 minus 9, 2, and 6 minus 2 is 4. So you have 429. Just like addition, that's not the only way you could have done that problem. Before borrowing became the popular way of doing it, one of the ways of doing it would look like this. 7 minus 2 is 5. 2 minus 9 can't be done, so we take from the 5. That's a 4. This is 12. 12 minus 9 is 3. 4 minus 5 can't be done, so we take from the 3. That's a 2. This is a 14. 14 minus 5 is 9. You can see we get to the same answer. Maybe a little bit clumsier. And again, my point is that there's not just one method. If you have a method of adding, subtracting, or doing anything that we work on in here that's different from what I show you, come and talk to me and I'll take a look at it and I'll make sure it is something that works every time. And if it is, feel free to do it that way. I mean, math is about what makes sense to you and what you're going to be able to remember how to do, not what I can make you memorize and repeat on a test in 2 weeks and then never remember again in your life. Again, I'm a realist. I realize that on something like this, you're going to look at this and say, hey, okay, that's about 700. That's about 300. 7 minus 3 is 4. That's about 400. Now, I want to make a little bit of a note here about those estimates. The quick estimates I've been doing, like I said, I hope that you come up with your own way of estimating so that it works for you and you're more likely to do it. But the estimates I've been doing work out well because the numbers have the same number of digits. So these both, their first digit is hundreds. So when I round it, this will be 700, this will be 400. All I have to do is add or subtract those first digits. Here it's adding, so 7 plus 4 is 11. Then keep it hundreds, put the same number of zeros on the end. If it were something like this, however, it's not so simple because they're not going to be rounded the same place. Again, whatever is going to work easiest for you. You could round this as 2,000 and this is 600 and say, hey, I'm expecting something close to 2,600. That's fine. You could round this and say, hey, that's about 2,300. This is about 600. 23 and 6 make 9. That's 29, something close to 2,900. Notice those estimates are very different, but they're just estimates. Whatever method works for you, you just have to know that when you get to the answer, okay, this one was rounded a lot further, so there's a good chance my answer is going to be further away from it. Anyway, let's look at multiplication. Let's do 31 times 23. I'm going to go ahead and I'm going to write this out in its full form now. So 31 is 3 tens and 1 1. 23 is 2 tens and 3 ones. When we multiply, do we need to have the same name? No, we don't. So what that means here is this 3 tens not only can be combined with the 2 tens, but it can also be combined with the 3 ones. In fact, every digit in the top number can be combined with every digit in the bottom number. And that's really all that our long multiplication is. It's just an organized way of making sure every digit in the top number gets combined with every digit in the bottom number. To do that, depending on where you were taught and what method you were taught, you pick a digit and you start with it. The one that most of us have been taught to start with is on the bottom number and the last digit, so the 3 ones. There are different regions depending on what part of the country you went to school in and whatever. They'll start with the last digit of the top number or whatever. It all works out the same. So anyway, we start with the 3 ones, and we're going to multiply that by the last digit of the top number, the 1 1. Just like any other multiplication, we combine the counts. What's 3 times 1? 3, and then we combine the names. 1s times 1s, just 1s. 1 squared is just 1. Then we have the 3 1s times the 3 10s. 3 times 3 is 9. 10s times 1s is 10s. So now that we've used that the 3 1s, we've multiplied every digit in the other number by it, we're going to move over to the next digit. What have we been taught to do down here before we move over? Put in a 0 or leave a space or whatever there, right? The reason for that will become apparent right in this next step. So if we're using the 2 10s, we got 2 10s times 1 1. Combining the counts, 2 times 1 is 2. 10s times 1s is 10s. Putting that 0 there just made sure that we're lining up our columns with the like place values. Then 2 10s times 3 10s. 2 times 3 is 6. 10s times 10s. 10 squared or 100. Hundreds. So then we got our columns are lined up. We can just combine the things with the same place value. 3 and 0 is just 3. 9 tens and 2 tens is 11, so it's 1, carry the 1. And 1 and 6 makes 700, so 713. So you can see with the place values written in there, all that process, everything we did in long multiplication is just a matter of combining everything and then lining up the stuff that has the same place value so we can combine it later. Now again, I realize that long multiplication is not something you're going to do a lot of by hand. So before you punch this in the calculator, once more I would ask that you do something like this. That's about 30. This is about 20. 3 times 2 is 6. Now the difference is when you're multiplying, you combine the names, right? So this doesn't stay tens, it's tens times tens or hundreds. The shortcut when you're multiplying estimates like this, 1 0, 2 zeros in the problem, 1 0, 2 zeros in my answer. You do have to be a little bit careful with that. Let's do some examples here. Let's say I have 7,000 times 400. I would do 7 times 4 is 28. How many zeros do I need? 1, 2, 3, 4, 5. Exactly. Put in my commas, that's 2,800,000. Where it can get a little confusing is when you run into something like this. 50,000 times 80. 5 times 8 is 40. We have 1, 2, 3, 4, 5 zeros. Is that enough? I've got 5 zeros there. No. That 0 was with the 40. That 0 came from the 5 and 8. We'd have to have 5 more zeros on the end. So that's 4 million even. Now again, that's how I estimate. You guys may come up with a different way of estimating those that makes sense. You know, for me, I'm just looking at that, getting that quick 600, realizing 713. It's a little ways away, but both of my numbers here were rounded down, so I'm expecting my answer to be bigger than my 600.
Sometimes it's easy just to put the 0 first.
Yeah.
Then multiply the number. So
Yep. Yep. Sometimes it is just to take these zeros and say, okay, that's 5 zeros, and then 5 times 8 is 40, so I put 40 on the front of it. Yes, good point. Okay, before we move on to division, I want to point out a couple little things about multiplication. We did the long multiplication, but we didn't really define what it means to multiply. I'm kind of relying on your memory that you've memorized your multiplication tables here. But if we look at something like 5 times 3, now all of us now know that that's 15, but if you think back to like first grade or so, when you were just learning how to multiply, before you memorized your multiplication facts and you knew that 5 times 3 was 15, how did you figure that out? There you go. 5 plus 5 plus 5. Repeated addition. It's 3 5s added together. It's 5 3 times. Gave us 15. Now, I made a big deal yesterday about multiplication and division following the same rules. One's going forward, one's going in reverse. So multiplication is repeated addition. It makes sense then that division is repeated subtraction. If I have 24 divided by 8, that's asking me how many times can I subtract 8 from 24? I subtract it once, I get 16. Subtract it again, I'm at 8. Subtract it again, I'm at 0. I subtracted 8 1, 2, 3 times. So 24 divided by 8 is 3, because we can subtract 8 from it 3 times. We can run into something like 32 divided by 7. So we subtract 7 from 32, we get 25. Subtract 7 again, we get 18. Subtract it again, we get 11. Subtract it again, we're at 4. We can't subtract it again, can we? We subtracted 7 1, 2, 3, 4 times, and there was 4 left over. So 32 divided by 7 is 4. with a remainder of 4 because we can subtract 7 4 times with 4 left over. Now, there are cases out there, there are situations out there where we'd rather have that remainder. Especially when we look at fractions, we're going to see that situation. Your calculator won't give you a remainder. You divide this on your calculator, 32 divided by 7, you're going to get something like 4.57142286, approximately. I can keep going if you want me to. Don't worry, it's not contagious. No. So yeah, looking at the calculator, it gives you that decimal. How do you figure out what that remainder is? And that's something we'll look at when we do fractions. I'll show you a way to get that to work. So anyway, we have this concept now that division is just repeated subtraction. So now let's go ahead and take a look at long division. Let's take something like 68,592 divided by 21. Well, even though I just said it, I'm not about to start subtracting 21 from 68,000. I don't have that kind of free time, right? But let's take a look at a little bit simpler example. If I were, let's say I'm just taking 25 divided by 2. If I want to subtract 2 from 25, I can take my 25 and subtract a bundle of 2. I can take 10 2s, which is 20, and subtract it. Now I've subtracted that 2 10 times. I've done it all at once. It sped up the process. So if I could subtract bundles of 21 down here, it would make this go faster, wouldn't it? That's all long division is it's an organized way of subtracting that number in large bundles. How big of a bundle? Well, we look at our place values of the number we're dividing. What's the place value of that first digit? 10,000. So let's try a bundle of 10,000 21s. 10,000 times 21 is 210,000. Can I subtract that? No, it's too big. So I cannot subtract a bundle of 10,000 21s. So I go to the next place value, which would be 1,000. 1,000 times 21 is 21,000. Can I subtract that? Yeah, I can. Now, what I really should do is I should do something like this, where I'm going to subtract 21,000, that's once. Subtract 21,000 again, that's twice. I see here I can subtract it several times. To shorten this up, how many times can I subtract 21,000? 3. 21,000 times 3 is 63,000. Those are 2, 9, 5, and 5. So what I just did here is I subtracted 1,000 21s 3 times. That's 1,000 times 3, or 3,000 21s that I just subtracted. Does that make sense? I just subtracted a bundle of 3,000 of them. A little bit quicker than subtracting it 3,000 times. So the next place value is 100. 100 times 21 is 2,100. Can I subtract that from what's left? Yes, I can. In fact, I'd say twice. 2,100 times 2 is 4,200. Leaves me with 2, 9, 3, and 1. So again, I just subtracted a bundle of 100 twice. So that's 100 times 2, or 221s. Next place value is 10. 10 times 21 is 210. I can subtract that. Looks like 6 times. Yeah, 1,260. 2, 3, 1. 132 left. So I just subtracted 10 times 6, or 60 21s. And of course, all that's left now is 21. Looks like 21 times 6 is going to be 126. Leaves me with 6 left over. So 1 times 6 is just 6 times. So I just subtracted 21 3,266 times. And I had a remainder of 6 left over. So 68,592 divided by 21 is 3,266, where the remainder is 6. Now you might be looking at that thinking, okay, interesting, but that looks nothing like what I was taught for long division. And at first glance, it doesn't look anything like it, but it's actually exactly the process. Let me show you. All that what we've been taught is a shortening, an abbreviation of this process. We were taught to do this. You take your 21, does 21 go into 6? No, right? So you leave it blank here. That's exactly what we did here. We took the place value of the 6 was 10,000. 10,000 times 21 was too big. We couldn't subtract it, so we left it blank. We went to the next place value. Next place value is the 8. Does 21 go into 68? 3 times. So the 8's the last digit we used. We put the 3 above the 8. 3 times 21 is 63. We subtract to get 5. Well, what we just did there is what we did here. 21,000 times 3 is 63,000. Put the 3 up. All we did is we left off all these zeros here. Now, since we didn't have those zeros, we didn't bring down the 5, 9, and 2. So in this process, we bring down the next digit, which is the 5. Now, most of us are taught just to bring down the digit. I always put this arrow in. That way I can trace back what digit I brought down. That way a lot of mistakes get made because you miss it. You bring down the 5, and then the next time you bring down the 2 and you skip the 9. So those arrows help you trace back what you brought down and what's still up there. But you can see how this is still very, very similar. I'm just leaving off all these zeros at the end here. Now 21 into 55 is twice. 2 times 21 is 42. Again, exactly what I did here, only I'm leaving off the zero. Now I don't need to finish that process. This is going to end up just the same as it did here, but you guys get the picture. So all of these processes, and the reason I'm going through all this stuff in detail, I know you guys know how to add, subtract, multiply, and divide, but most of what you've been taught in math is just a severe shortcut of the real process. It's been abbreviated to make it easier, cut down to take less paper and less time and make it faster. But if you take the time to go back and see the long method of what's going on, the long version, it explains a little bit more of why things happen. So when we get into the algebraic numbers, they're going to be a little easier to work with because we understand how numbers interact. Now, like I said, I'm a realist. I realize that on something like this, I mean, long division is the one operation I try not to do by hand if I can avoid it. So I would be punching this in a calculator. But you're looking at, okay, that's about 70,000 divided by about 20. Now, when we multiplied, we combine the zeros. When we divide, cancel out the zeros. So we cancel out 1. 7 doesn't divide by 2 really well, does it? So there's a couple of things. Like I said, estimating is something you have to figure out a method for yourself. I'll show you a couple of different possibilities here. The way I would do this is instead of doing the 7, I'd do the 70. 70 divided by 2 is 35, and then add the 2 zeros on it, 3,500. Another way of estimating that same problem. I would still cancel out the 0, but you might do this. Like you had said, sometimes it's easier to write down the zeros first. I have 3 zeros left. Well, 7 divided by 2, it's bigger than 3 and smaller than 4, right? Between 3 and 4. So I know that my answer is between 3 and 4,000. It's an estimate. I don't have to be exact. I can come up with a range rather than a single number. So like I said, when it comes to these estimates, figure out what works for you. Anybody have any questions? Okay, well, it's a little bit earlier than I would normally finish up class, but this is a little bit longer assignment, being easier problems. You guys have your little book with you? Okay. In that small book, units 1, 2, 3, and 4 are just applied problems with addition, subtraction, multiplication, and division. Now, When I give these assignments, it's almost always implied that I only want you to do the odd numbered problems, so 1, 3, 5, 7, 9. The reason for that is if you look at the back of your book, the answers are in there for the odd numbered problems. As I mentioned yesterday, I don't collect homework and grade it because I just don't have the time. Also, like I said, the homework is for you to learn. So I hope that you're checking over your answers in the back of the book. My suggestion is you do 1 or 2 problems and then you check the answers in back before you do any more. I hate to have students do a whole assignment only to get done with the whole thing and realize they're doing it wrong, because now they've developed a bad habit. Now they've got to forget how they were doing it and learn the right way, and I don't want you to do that. So I do suggest you do a problem or 2 and then check it. If you get one wrong, try to figure out what you did wrong. If you can't, that's where we start our next class, is I'll answer questions on problems with the homework. So units 1, 2, 3, and 4, the odds. That's a little bit longer than normal. I apologize for that. But at the beginning of the class, we move a little fast here.